controls. Okay,
Yeah, yeah.
Started?
Yeah.
Okay, welcome everybody. And today we would like to talk about the application of laws governing nature to social science. And let me start with a review of first law of thermodynamics. And many of you are familiar with that. It's called energy conservation. It's essentially governing for a closed system. If you have energy switching from one form to another, for example, pendulum, energy switching from potential, gravitational potential energy to kinetic form, right? And you imagine without cost, without dissipation of energy to the surrounding, it will go back and forth forever. And light is a combination of electrical form of energy and magnetic form of energy. And energy does swing back and forth, right? And of course, you also have the energy switching from mechanical form, for example, thermal energy, the heat, to chemical side, or vice versa. When you have a chemical reaction, some of them are endothermic, some of them are exothermic, generating heat or observing heat. Okay, and that is the first law of thermodynamics, very well said, but unfortunately people tend to ignore the second law of thermodynamics. Second law of thermodynamics tells you when you transfer energy from one form to another, there's always a cost involved. Sometimes it's significant, right? And there's always friction, dissipation of the energy in acoustic form, noise, right? And they will always involve some of the cost. And we can take special measure to minimize such cost, but you cannot eliminate such cost. The second law of thermodynamics. And in society we have a saying called no free lunch.
Right.
That's similar to the understanding of second law of thermodynamics. In fact, I always question the wisdom of governor returning a tax. It is not a wise decision. Why? To collect tax from individuals, it takes a lot of effort, administrative cost. And then you decided to give the tax back. You may think the taxpayers get the money back, it's good, but in the process, you are wasting taxpayers' money, right? There's a cost involved giving that back. I would rather government to invest in education and other aspects. The money is already collected, and if you return, that's not very good. It's like driving the vehicle to and from the target, and you have frictions both ways. Okay? Now, you're all familiar with Newton's law, right? The famous second law, Newton's second law, F equal to ma. And Newton's law gives you a very nice governing equation for motion. And up until 19th century, people think with Newton's law they can really understand how planets move and how objects move, and they are often following a deterministic trajectory. And in fact, even the mighty Einstein had a famous saying. He said, God does not play dice. You remember? And he had an argument with Niels Bohr about quantum mechanics. He could not understand. Everything should be deterministic. He has this wonderful relativity theory to tell you how the space and time can be also regulated given the speed of light, given the traveling velocity. And he failed to recognize the second law of thermodynamics. Why I say so? Because when you have deterministic equations, let's say 3 first order, I will show you that equation. It's very simple. Three first order ordinary differential equations. Three equations coupled together. And one scientist in 1950s from geoscience in MIT, Edward Lorenz, discovered he's playing with that simple set of equations. And he discovered that the solutions never repeat itself. The pattern looks the same, but it never, if you follow the time snapshot, never repeats itself. And he discovered the chaotic behavior of simple dynamic system, coupled dynamic system. Mathematicians were also puzzled in 19th century. Henri Poincaré, the famous French mathematician, actually also studied the same phenomena and discovered very interestingly, in the phase space, you have three unknowns. If you plot three axes representing three unknowns, every time instant, you have one space, 1 point in the space. So you follow the trajectory, that's called the phase diagram. You will see these trajectories are very close to each other. And the reason why they are so close is because they have interactions, the mathematical equations, they are coupled. But because they are so close to each other, it's prone to perturbation. It's very important to see chaotic behavior derived from deterministic equations. However, for these equations really to be solved either mathematically or numerically, and you always introduce perturbations. How do you represent number in computer? Do you guys really think computer can represent number precisely? You know, up to a certain accuracy. In 1980s, when I was a student, that's a single precision, 10 to the power of minus 8. In 1990s, when I started to teach, that was a double precision, 10 to the power of minus 16. Now, here is quadruple precision, 10 to the power of minus 32. But even 10 to the power of minus 32 is a small number, right? But what happens is, if you have a positive Lyapunov exponent, you will learn this from ordinary differential equation, within finite time, even 10 to the power of minus 32 will grow to a tremendously large number. Okay, that's the reason why we have chaotic behavior. Because of chaotic behavior, actually, as a result, you may think God does play dice, a lot of random influence, right? Because of chaotic behavior. So you do see unpredictable phenomena, random phenomena. In fact, there's a definition for true random phenomena is the Lyapunov exponent goes to infinity. If the Lyapunov exponent is a little bit larger than 0, it is chaotic system. If it's very, very large, within a split of a second, you diverge very quickly and looks to you like it's random, right? So in a way, I can see in social science, people like to use statistical method. In natural science, people like to use deterministic method, reductionism. Isolate the system, study them precisely. But right now, with the aid of computer modeling, I will show you some fancy computer modeling. Both sides are pushing to the middle. Okay, and natural scientists, engineers, physicists, they want to understand more and more the effect of noise, perturbations. Social scientists, they want to know more and more the deterministic aspect in complicated societies. A key example is economics. Right? A lot of Nobel laureates, they are mathematicians. In fact, I met John Nash myself in one of the gatherings in Princeton. There's an MIT club in Princeton. I went to that social occasion. I sit with him for quite a few hours with his wife and his son, and talking about economic system. He perceived economic system just like mathematical models, right? And there's a famous Nash equilibrium, and of course that was already done when he was a student. Now people understand we have to move beyond that equilibrium, right? There's stochastic modeling for Planck equations and all these fancy mathematical models. People think they are the culprit of economic crisis. I don't think so. And they actually blame one particular engineer in Wall Street. He probably had a mistake in his model. I don't think so. Actually, before the modern economists try to understand the behavior of market, of economy, I think the society was going through up and downs very violently. For example, in 1920s, there's a Great Depression. And what happened with Great Depression, now we understood, was because a very simple fact of lack of circulation of currency. At that time, everything traced back to one single entity. It's called gold. Right? That's everybody accepted currency. But unfortunately, after the first industrial revolution, we're still making locomotive, railway systems, even automobiles, and so at the beginning of 20th century, the productivity of society dramatically increased. Unfortunately, the amount of currency is this level because you have a limit of resources, natural resources to dig the gold, right? And so they don't match. So nobody has the money. $1 at that time was a lot of money. And they don't know how to handle this problem. And the president at that time was Herbert Hoover. Unfortunately, he's a civil engineer from Stanford. He failed to understand economic system. He's an engineer. At that time, they don't even know chaos, no terminology like fractals, no terminology like complexity. So he said he wanted to use the ancient wisdom studied from Adam Smith. Leave it to invisible hand, leave it to God. So what's the result? And nobody has the money to purchase the good. The society has a tremendous productivity, produce milk, crops, but nobody has money to purchase, so they lay waste, throw it away. And as a consequence, the vicious cycle starts. When the farmers cannot sell their product, they cannot get money. So they start to lose their property, and finally, we have to wait until a very strong-hand President FDR to resolve the problem. Actually, the problem was finally resolved during the Second World War. And now we understand this better. And if there's no government intervention, a natural phenomenon will be a big rich and poor gap. Okay, that's called power law distribution. I will show you very quickly. I'll go through the slides. You will see that magic power law distribution is produced in all complex systems, not only for economic system, but also for biology. Some of you are biology major. There's an interesting power law distribution called the Glaber's law. It's metabolic rate as a function of body mass. From amoeba all the way to the elephant, they follow the same path. It's magic power law. The metabolic rate related to body mass, the power is 3/4. Some mathematicians actually prove it is from nonlinear dynamics, from fractal dimensions. Okay, and that power law distribution was also independently discovered by the Italian engineer, Pareto. It's called the Pareto 80-20 principle. In computer science major, they know this Pareto optimizations and 80-20 principle. And essentially tells you 20% of the population govern 80% of the wealth. Okay? It's a naturally evolved result. No conspiracy theory. It's just, if there's no government intervention, you will have that power law distribution. And if there's no government intervention, that distribution eventually in the history happened many times in China, in Europe, will lead to social chaos, revolution, change of dynasties, right? Economic crisis. And now we know better. I think a few years ago there was a price started from Wall Street. We immediately recognized that might be the same problem in 1920s. Mm-hmm. Why? Because right before that there was the information technology boom. The productivity of society dramatically increased. And suppose this is productivity and this is the level of currency. If the level of currency is this, you have a devaluation of the currency, right? If the level of currency is this, you have what's that called? Deflation. Essentially, you need more money. Mm-hmm. And I think when we have that crisis, actually they made the right. I think they made the right decision. They invented a term called quantitatively easy. So President Obama started the QE1, QE2, QE3, essentially print out billions of dollars. Right? That's a fancy name of printing out money. Federal Reserve authorized this. And as a result, you can see we don't have much inflation. You may imagine if they print out money, there will be inflation like this. No, it's catching up, right? And now the question is, do you really know the level of gross domestic product? No. There's a geographic difference. It is global village, and the sensor data is not accurate. So it's always a rough estimate. But at least now we understand how markets swing back and forth. We can take preemptive measures and help. But there's also another downside. Because we understand the market very well, and smart people in Wall Street, they can actually intentionally trigger some perturbation, and they can make money. Up and down, they do make money. And I hope they don't cause tremendous trouble, and there must be regulations for their behaviors, and they do gain the market. They are smart people. And when I was a student at MIT, many of my fellow classmates, they were tapped at Wall Street. They recruit on campus. And all you have to do is pass the IQ test. They talk to you and measure your IQ. They literally do. And then if you pass their test, you work for them. And they make a lot of money. Okay, so that's one application of complexity, chaotic system in social science. And there are a lot more. And in fact, what I'm going to show you the slides later, but I'm going to show you one example is related with Chinese culture, American culture. And I've been thinking about this for many, many years. And I live half of my life in China, half of my life here. And the reason why this society functions very well is because it is bottom-up, community-based. Right? Everywhere I go, I visit most of the states, a lot of communities. They're all similar to Wichita Falls. I mean, they're all more or less the same. You see churches organize the community, people do volunteering work, and through that volunteering work, and organizations in the church level, gradually they develop a sense of self-governance, right? And then you can see if they really have ambition, ability, they can run for Congress, state legislators representing the state. Eventually they go to the national level representing their district. It is completely different from Chinese social structures. In China, I can ask my fellow student John, he can tell you the same thing. People wait for orders from top. The structure, governing structure is top down. Yeah. And if you have a very good leader, you will see society is functioning and producing, productive, very nice. But unfortunately, there's always a second law of thermodynamics at play. You cannot guarantee that they always make right decisions. Right? What if they make wrong decisions? Then there will be chaos. Seriously, there will be war, broke up, and then the dynastic change again. It goes through this type of cycles. And I often have an analogy of Chinese social structure. It is like a forest with one tree, gigantic tree, beautiful. But unfortunately, in nature, there will be disease. There will be weather changes. That tree will eventually perish. And then there's another tree growing up gradually, and it's beautiful again. And that's what happens with dynastic change over a few hundred years. But here is more, I would say, more ductile. The society in New York, you may see a lot more people are Catholics. Jewish people, they may be thinking a little bit different, worship in a different ways. Here, more Baptist, Methodist. I'm a Methodist myself. And I call this different Christian orientations. Right? And they may have different orientations, but they are all metals. Right? That's the structure of metal. We have different grains. Within the grain, you have different orientations. Between the grain, you have grain boundaries. So you can see metal is strong. It's also ductile. Suppose there's a fracture coming in from one crystal, because dislocations. There's always defect in materials. Why we have defect? Again, it's second law of thermodynamics. You cannot have a perfect crystal for big size. Imagine diamonds, they are precious because they are small. You cannot have diamond as big as a table. Under the Earth's condition, it's impossible. But if there's a planet with a gigantic force field, it's possible, but for that gigantic force field, it's still small, comparable, right? And I think because there's a defect, there's always dislocation, and dislocation will fracture the grain occasionally. Society, they always some dislocations, disagreement, violence broken out. Then you have a grain boundary. So propagate, you have a grain boundary to arrest that propagation of fracture. So eventually it will stop somewhere, right? For example, if a Muslim community is disagree with another neighbor, Christian community, it could happen, conflict break up, and then eventually will be arrested by other communities, contained. Arrested is a special terminology for fracture, propagation, arrest. But in Chinese society is more amorphous, like ceramic structure. I have illustrative picture to show you. It's like there's no long distance order. Individual family together. It is also strong ceramics, glass, right, and ceramics. They are very strong. But the problem they have is if there's a defect, fracture coming up, it will keep on propagating because all the other communities, they are the same. There's no way you can stop the propagation of the crack. Because if the crack starts from here, the next community is identical. The next one is identical. There's no way to observe that impact of energy. And of course, can we change? Can they learn from each other? I think so. With the information technology, people are more open. You have students coming from China, you have students going to China, and you have students getting American degrees and work in China. So the cultures, the information, they do mix together. What is the law governing the mixing? Again, there's a law in natural science. It's called Fick's law, diffusion. Right? Diffusion of heat, diffusion of mass. It is also the same thing. The ideas, culture, they also diffuse. Technology also diffuse, right? From the United States, the information technology diffuse all over the world. And I hope someday, I think people can learn from each other. There's always room for improvement. No system is really perfect. Can you say metal is better than ceramic? Maybe sometimes it's better, but I think in the airplane, right now we tend to use composite. The reason for using composite, taking advantage of different materials, right? Okay, I think enough for my talking. Let me go through some of the slides, then we can talk more. How much time do I have?
Their side, yeah.
Okay, and I want to go through some of the applications of computer programs. And in fact, right now engineering design is very much simulation based. You know, this is a carbon nanotube and buckyball, and people want to use this type of thing as a new electronic device. And you can model the deposit of atoms layer by layer, but you also have to pay attention to the second law of thermodynamics. And all these design of pressure vessels, you can use SolidWorks and ANSYS, Ardina to predict the stress behavior. And the entire bridge, this is the Bay Bridge in San Francisco, has to be simulated. That's a state law from California by a certain software called Ardina. And missile launching process, and all these things are done in a computer simulation. Roof crashing, rolling test of a vehicle, and even the engine. I think the simulation is very big, probably. I'm not sure quickly. And this is the airplane crashing into the concrete. This type of particular research, of course, showed up because we want to protect ourselves, and also armament. And in biomedical engineering, we can use fine elements to model how to retrieve kidney stones. And metal forming process, you can also model. The stamping process to form different shape for automobiles. And you can simulate before you actually do it. Very precisely. But one thing we are still trying to accomplish is to handle the polymer. Everybody knows polymer folding is a complicated subject, but you have to study. Why? Because the shape of polymer defines the property. And unfortunately, that shape is three-dimensional. And it is actually very prone to the environment perturbations because polymer itself is molecular level and very small, and they have so many substructures from alpha, beta sheets, that's primary structure, that secondary structure to tertiary. Primary structure is, of course, long chain polymer, a string. To quaternary structure for hemoglobin, very difficult. And I did a project with one of my PhD students, Dr. Tao Wu. He got a PhD under my supervision. He's now working in Microsoft, focusing on parallel computing. And I think this is the struggle we have. You can see the interesting phenomena is always for hemoglobin polymer, for sickle cell anemia studies is around hours. But to study polymer, you have to use molecular dynamics. The time step is 10 to the power of minus 15 femtoseconds. So you can see from femtoseconds all the way to 1,000 seconds. That's a lot of scale jump. Right now, nobody can do that. At most, you can only do nanosecond. Maybe if you go to Los Alamos National Lab, Sandia National Lab, you use a tremendous national resources, you can compute up to milliseconds. That's what last time I was in Los Alamos attending. They say they can calculate up to milliseconds. But now I want to tell you how expensive that calculation is. To maintain 2,000 processors at the MSU, let's say we purchase 2,000 processors, the electricity bill is $500,000 a year. Okay, think about this. Sandia, they have 20,000 processors, maybe more, and the electricity cost is tremendous. And still, it's a challenging problem. And in engineering design, you also have to sweep through parametric space to find out to optimize the design. So there are a lot of variability. It's a big challenge still to scientists and engineers. And these are the this is already out of date. To solve 1.5 million equations, it takes about, I think 10 years ago, roughly 4 hours. Right now, maybe half an hour. But still, it is a long time. You have to, for nonlinear problem, you have to solve this many, many times. Okay, and this is the research I did for hemoglobin. So like, we have a normal hemoglobin, they separate as a bead. But when you have a sickle cell anemia, they tend to agglomerate, become a rod, and then essentially make the membrane very stiff. So this is a genetic mutation from GAT to GTG. That's one mutation. In fact, sickle cell anemia is the first disease we can pinpoint to mutation at the genetic level. And because it's a well-known disease. And because of this mutation, one section of this quaternary structure changed from hydrophilic to hydrophobic. And then as a consequence, when you have the oxygenated state, they have a kink. So this hydrophobic side match with that side, so you can form the chain. Okay? And essentially the chain will make the sickle cell hemoglobin very stiff. And this is the molecular dynamics simulation. I'm not sure if I can make it wrong. This is the movie produced by my student. Probably, it's okay, it's not important. You can see this type of simulation. We spent 3 months in a parallel computer cluster. Nobody ever repeated it, actually. That's the only result available. So it was published about 4 years ago. Still, we haven't seen anybody repeat that result yet. And this is my one slide overview of my view of science and technology. I think 17th century, we have classical mechanics, Newton, right? And James Clerk Maxwell was born in 1831. That's the year Michael Faraday discovered the electromagnetic induction. and he died 48 years later. And there will be 1879, I think. That's the year Albert Einstein was born. So he's a transition figure. And Albert Einstein, of course, everybody knows relativity theory, modern physics, actually quantum mechanics was developed by Niels Bohr. And then dynamical system, I think early 19th century, Henri Poincare, the mathematician, recognized they can give you unpredictable behavior. But really in 1980s, because of the computer development, so people can solve problems very efficiently. In the time of Henri Poincare, he recognized mathematically there's an issue with the folding of phase diagram. And then 1980s, people start to produce a lot of beautiful chaotic systems with different fractal dimensions. And now, to make, this is only 3 or 4 equations. Now with the modern parallel computing technology, we go to complex systems, big. And there's a possibility for us to maybe handle some of the simple social problems we can tackle. And of course, to do any modeling, so you study with Schrödinger equation, right? And get the bulk nucleus location settled, and then you go look at the electronic state, molecular interaction, Coulombic interactions. And for chemists, they know they have strong and weak interactions. Okay, we still have a few minutes, so let me quickly go through the interesting things. These are the Brownian motions. This is actually going back to my PhD thesis. And now you can see these very simple 3 equations gave you this chaotic behavior. I want to say chaotic means if you look at the time history, they never repeat itself, but the pattern is fixed, right? And if you look at the snapshot, they are really different. But overall, the pattern is the same. You see, the only thing different is a little bit perturbation right here. The rest is the same. You take any time snapshot, it will be completely different. But overall, the pattern is the same. That is actually the challenge for weather forecasting. You can never forecast for a long time, but you can accurately do a weather forecasting for a few days. Okay, this is all because of this Wiener process, it's stochastic, and you have some diffusion aspects. I think the previous Yale student did a good job, and they produced these results. And Wiener process, only one process generating white noise, but there are different type of noise, right? White noise happen to relate to diffusion, but there are different type of noise. You can see alpha can go from 0 to 1, and you can play with that. For different systems, they may have different noise. Here's the metabolic theory of ecology, and this set of slides was produced by an undergraduate student working with me a couple of years ago, just for fun. And I want to show you that interesting relationship. Metabolic rate is proportional to the body mass to the power of 3 to 4. And this type of power law distribution is prevalent in complex systems. Okay? And you can Google, just type in Glaber's rule, and you can find a lot more information here. This is the basic line. Some of the power law distribution, if it's negative, it goes like this. Okay? Some explanation of that. Okay? And these are the fractal geometries. In 1980s, people used this very simple iterative map to reproduce tree-like structures using fractal dimensions. Okay. I'll leave you this Pareto principle 2080. Slide. I missed that slide. The slide I want to show you the Chinese social structure and the American social structure, but it's okay. You can see it's metal and ceramic. You can Google it. This is what I have so far with respect to application of laws governing nature to social science. And we can, for those students who are interested in this type of research, we can come up with a very focused area and to see if we can apply, for example, second law of thermodynamics to understand the boundary behavior. And we can start small. Okay, we don't have to have this is my big ambition, but we can always start small, accumulate. Okay. Yeah, thank you for your attention.
Thank you.